So our next speaker is Dianne Mitchinson. She's actually taken on 2 talks. Her first talk is for Bruce McMonnies from BHEM Geoscience, and it's titled Multi-disciplinary 3D Data Integration at Snow Lake. Her second talk that she'll talk to, the one that she was supposed to give, was district-scale 3D targeting over Chisel and Lalor properties using multidisciplinary criteria and weights of evidence methods. Dianne is a senior consultant at Mere Geoscience, overseeing integration and interpretation of multiple disciplinary geoscience data and leading mineral exploration targeting projects. Dianne obtained a PhD and completed postdoctoral work with the Mineral Deposits Research Unit at the University of British Columbia, where research focused on characterizing physical rock properties in orogenic gold and porphyry deposit settings for the purpose of improved interpretation and modeling of geophysical data.
Thank you, Peter and Dennis and BCGS for having me and Bruce speak today. And I'm happy to present Bruce's talk before my own. He's traveling right now, so he was unable to present this himself. But the work leads directly into the targeting work that I'm going to be presenting afterward. He wanted me to say that this work here that I'm presenting is the result of a real excellent directed effort over 3 years of finding, he said, and compilation, integration, interpretation of all of this excellent data that we're seeing from the Lalor deposit, but not just the Lalor deposit, but within the Chisel Basin, and finally targeting on that data to bring it all together. So with that, I'm going to try to do my best here and present Bruce's talk. So the presentation outline, a bit of background on the project, the exploration goal, Hudbay's exploration objectives and the objectives for doing this 3D multidisciplinary integration project. And then sort of the meat of the project, the geological model building, the borehole physical rock property analysis and interpretation. And Vince, this is the same work that Vince talked about yesterday. The clustering analysis on the physical rock property data and geochemical data. And then 3D constraint inversions, and then finally targeting, and then some conclusions. So the project background, so Hudbay Minerals were obviously successfully exploring within the Snow Lake Greenstone Belt for many years, and most of the discoveries are attributed to using geophysics, as we've heard today, and to locate the conductors for drilling. And this is also often followed up by the borehole and sort of localized modeling to direct the follow-up drilling. Over the time period, a significant amount of geoscientific data was acquired, as we've seen. And if this data is compiled on a similar platform, or the same platform, using a single projection datum, the data obviously could enhance our overall understanding of the mining camp. And so the aim of this project is to leverage the wealth of information that is acquired at significant costs, obviously, and to better target sulfide mineralization. And so he says here, the tipping point was finding the appropriate person to run with the project and make it happen. That was Bruce. And he really was, he got involved in this project. He really pushed it forward, was really the link between Hudbay and getting all that data together, and the link to the contractors and acquisition people that were involved collecting the data in order to amass this data and come up with this really excellent integrated model. So the exploration goal was to develop this 3D multidisciplinary data model with the objective to understand and provide knowledge of the Lalor VMS deposit, to compare it with other known deposits in the area, and to identify new targets. So the model here, this is just a snapshot of it. There's the sort of transparent map and all the drilling, and you can see underneath all the surfaces, geological surfaces that were built and structures. And the extent of that was 10 by 10 by 3 kilometers, and the resolution of that, the grid cells were 50 meters by 50 meters by 25 meters, and then there's almost 5 million cells in the model. So the objectives, Hudbay objectives, were to integrate 3D multidisciplinary quantitative data to develop an exploration model consistent with data from many, many sources: geological sources, ore information, lithogeochemical information, geological or structural information, physical rock properties, geophysical surveys, and look at spatial relationships. This type of model allows you to look at spatial relationships between features and bringing in the constrained 3D geophysical inversion models. So this will lead to advanced understanding of geology and mineral deposits in the area, and then ultimately to better targets. So to get on to kind of the meat of the 3D geologic modeling process and data integration process, this is just some snapshots showing how the 3D geological model came together. And so this was a big effort involving the Hudbay and Alan Bales came in and created additional cross sections that were needed to try to really flesh out the 3D geological model. And so the drilling, we had cross sections and fault modeling, and everything was adhered to the drilling information. And finally, we build a surface geological model that eventually is rendered into a 3D block geological model. So this says the 3D geology surfaces, lithology, convex, and thrust. So the thrust, the controversial thrust, is included in the model. Some additional data that was included in the multidisciplinary model was a seismic section that extended up through the Chisel, and this was also discussed as part of this workshop. But there are some excellent consistencies with the mineral deposits with Chisel, and so this type of information helped with the generation of the geologic surfaces for the 3D model. The next stage was bringing in borehole rock properties. Vince discussed this work yesterday. The information provides high-resolution, multi-parameter, continuous in situ data that's quantitative. And this data helps improve geological understanding. It supplements traditional core log geology, picking out things that may not be visible to the eye, and it provides a direct link to geophysics, which helps us interpret geophysics. And it also helps us to do constrained inversion modeling or to do forward modeling. And it improves the overall exploration workflow, logging, interpretation, and modeling, ultimately leading to cost savings through informed decision making. So the downhole logging, the logistics, there were 17 boreholes logged, strategically chosen to match existing sections. The measurements were made at 20 centimeter intervals, and then there was the optical televiewer and an acoustic televiewer data as well, and then QA/QC applied. And these are all the different parameters that were measured down the hole. And these are just some images showing that data downhole. And so this one is magnetic susceptibility. So the reds are the high susceptibility values. And so some of them seem to correlate with parts of the ore body. And then there are some other high values up towards the surface may be representing mafic rocks or other magnetic rocks in the stratigraphic package. This is density, and of course there's an excellent correlation with the ore bodies. And then this one is conductivity, again, a really excellent correlation. Then we have the optical and acoustic televiewer data, really excellent data and very, very detailed. And it allows you to find structures, to get orientations of structures, and it actually helps you interpret your physical property data you can look at your physical property data profiles, and if you see anomalies and things like that that are not explained by your written geological logs, you can easily go back, look at these images, and maybe you're going to find a fracture or structure or something that you didn't pick up before. And these also have hydrogeology and geotechnical applications, where you can find structure and failures and things in the rocks that might become important during the mining process. This is a downhole logging, borehole logging data from the discovery hole. I'm not sure what the number of the hole is. You all know what it is. But this is the clustering. There's the lithology at the start of the section. And then this column here is physical property clustering, and then lithogeochemical clustering with increasing numbers of clusters used. So here we've got quite a few different clusters used to try to understand the physical property data. And Bruce just highlighted a few things on here. So he notes that this is a magnetic rhyolite section here, and if we go further down, there are some basalts that have different physical property characteristics, different conductivities, resistivities, and then there's a non-magnetic rhyolite. So you can see that the geochemical clustering has picked out the fact that this rhyolite is slightly different than this, and you can go back to the physical property data and see that the magnetic susceptibilities are higher for one, the resistivities are higher for one, and so they have slightly different physical property characteristics. The clustering has picked out structures, like I mentioned. This is an annealed fault zone, so it's identified some difference in the rock there based on geochemistry. And then differences in the physical property profiles for disseminated sulfides and massive sulfides. So one may be more conductive than the other. Massive sulfides may be more conductive, and disseminated may be less conductive. So this is the downhole geochemical clustering data, and you can see that it has a sort of a geological look to it. And some of the things he noted in his interpretations of this data was that, so the yellow colors are representing rhyolites and rhyodacite. The red has a Morb signature, and is probably the three-house basalt. And the blue is an enriched basalt, probably the Morb basalt. So he was noticing that this blue unit, this enriched basalt, exists in the footwall and in the hanging wall. You can see in some of the superficial data, and then also in some of the deeper data. So it's just adding to the interpretation of the geology of this deposit and area. And then the green is this powderhouse dacite, and again he said you can see the greens at depth correlating with the powderhouse dacite, and then also at the surface. So the footwall and the hanging wall rocks appear to be more complex than in this data, this clustering data, than some of the mapping or drilling might suggest. So the next step in the data integration effort was to bring in some geophysical inversion models. So inversion, we've been talking about that quite a bit, and basically the inversion is finding a model that fits a set of geophysical data compared to forward modeling, where you have a model and you're generating data based on that model. So the goal of inversion is to produce a reasonable model that, a reasonable model that can generate, I guess, the data given field observations and some knowledge of their errors. And he has some merits of inversion here. So it directly transforms geophysical data into rock property data. So this is where we can start to make that link to geology. Constrained inversion calculates a physical rock property distribution that will be consistent with the geophysical data set, and the value added is only as good as our understanding and expectation of physical property relationships in the relevant geological setting. So this is really important to really have a good handle on what the expected physical rock properties are of the geological setting that you're working in order to be able to appropriately constrain inversion. In general, there's definitely more of a need for 3D and constrained inversions, and Hudbay made a decision to carry out multiple 3D inversions using various geophysical data sets, and Dianne showed several of those in his talk. And then we can integrate these into our 3D geological model and structural model and geochemical model for an improved interpretation of what some of these conductors might mean. So the 3D geophysical inversions that were brought into this multidisciplinary model was borehole, 3D borehole inversion, ZTEM inversion, DCIP inversion over Chisel and over Lalor, MT inversion over Chisel and Lalor, and there was a VPMG constrained magnetic inversion and constrained gravity inversion for the basin. And then there was a Squid inversion that was done by UBC. So first of all, the borehole 3D inversion, Dianne was also talking about this, inverting this data as well, and there's a really excellent correlation between the known lenses of the ore body and the conductors. You can see coming along kind of two perpendicular sections here, and you can see that it lines up really excellently with the conductors there. And there are some interesting features that kind of head towards the surface. And I remember looking at this data with Bruce and kind of looking at the geology and the alteration downhole. And this could potentially represent, we were kind of throwing ideas around about it representing maybe alteration along stratigraphy or something like that, because the stratigraphy above these lenses is more vertical compared to below, which is more horizontal. So it follows the kind of more vertical stratigraphy above the lenses. And then we have some interesting things off to the sides and below. This is the borehole EM inversion rendered as an isosurface. I don't know what the cutoff is. And then that's sitting there with, it looks like a balloon animal or something. But the grid is a interpolated alteration index, sericite alteration index, I think. And so you can see in the core of the system, there's these high conductivities. And when you actually look in detail, you see that they're sort of, they cross-cut the lenses. So I wonder if there's some kind of something focusing these sort of currents that are sort of perpendicular cross-cutting the lenses. And then there are some there is some correlation with this alteration halo. So maybe some of this conductivity is related to alteration. Okay. This is the 3D Titan DCIP inversion, and this is Chisel, and so there was some lines done south of Chisel and then north, and this is just showing that, you know, coming off the end of Chisel, south end, we're seeing the conductivity, and then in a cross section you can see that there's a conductor that's picked up in the inversion that's heading off of the end of the lenses. And this is the same, well, it's a 3D Titan DCIP inversion conductivity model, and this is just up where photo is, and there's some conductors there just southwest of photo. And same in this image down here, you can see just sort of some sections through that model. You can see it's a little bit deeper. This is some more balloon animal pictures. It's the brown is the same model as what I was just showing, that borehole conductivity isosurface, and the green up here above this line is the DCIP conductivity, which is it's much shallower, and then the blue represents the Squid inversion. So you can see in some places there's correlations, like the Squid and the borehole IP are correlating here, and the Squid and IP, or the borehole, sorry, EM, correlate at the lenses, but then we have this deeper conductor that comes from the Squid inversion. And then on top of that, we have the red now is, or the pink, is a ZTEM inversion isosurface, and that correlates quite well with the borehole, with the general trend of the borehole EM conductors. And then the green now is the Titan MT inversion result, and you can see that correlates pretty well. It also picks up sort of a deeper feature similar to what the ZTEM sees. And I don't know, I was thinking earlier when Dianne was talking about this, if that could represent maybe some kind of alteration system below, because often we can get conductivity with alteration, or due to alteration. So, so that all of this work was brought together, all of this data was brought together, and several 3D inversion models were built and incorporated. And in the end, there was a targeting initiative using the 3D integrated data. And out of that came several targets, 22 targets, and Bruce has broken them down into conductive versus non-conductive targets. And this is a whole different story that I won't talk about now, but I will talk about in 2 minutes. And so what has been achieved? GoCAD, which is the platform that we use, provides a repository for all data collected within the model limits. And the seismic line was depth migrated to be brought into this model. Cluster analysis of the physical rock properties and lithogeochemical and assay results show 6 primary rock types. Inconsistencies with current geological model need to be visited. Electrical property 3D inversions were completed for each available data set. Each inversion validates, supports, and complements one another. I wouldn't say completely, but some of them complement each other. But as Dianne was saying, they're probably telling different stories. They're reading different different sources and different depths, and they're probably seeing different geological features. The Borehole EM 3D inversion provides the most detail as far as the 3D inversion models go. And 3D mineral potential mapping was applied in the end to the integrated data sets and models. And so the conclusions, geology is 3D, so we should bring all of our geological and geophysical and geochemical data in 3D. 3D geological models are simply much better using and honoring all the data, and we can improve our interpretations in this way. Geophysical survey data, physical rock properties, borehole logging data, lithogeochemistry, and constraint inversions are fundamental exploration data that should be visualized, interrogated, and understood in 3D. And this model, the result of this work, is dynamic, alive model, and it's continually evolving. It's not the final model, and it's not the final say, and but it exists, and it can be modified and updated as new data comes in, as new interpretations are made. Multidisciplinary models link and connect current personnel that are working at companies to the big picture, encouraging them to work towards the same goals and supporting each other. Resource estimation group, geophysicists, GIS people, geologists, and engineers. And a champion was required to make it happen. And Bruce is a champion, and he made it happen. Thank you. I can answer some questions, probably.
Go ahead.
Just when you, at the beginning, when you brought in your faults to the geology model, how did you actually do that? And you have, and was that brought in, are there problems with scaling so far as the faults are quite in one direction? How those merge together? Do you have scaling problems?
At the beginning of these kinds of projects, you have to, it's like when you make a geological map and you have to choose a scale, and with that comes choosing those geological units and structures, scale of structures that you're going to be able to represent. So the faults that were brought into this model are fairly, I'd say, district scale. And a lot of these, Megan was talking about the complex structural setting, and a lot of that complex structure can't really be represented very well at that kind of scale. Ernst is going to talk later a bit more about geological modeling at the scale of Lalor. So I was saying to him it would be really interesting to try to correlate this model with the regional one and try to make sure that some of those important things are represented at the bigger scale if it's possible. Oh, thank you. Shall I begin?